Hello, math people. Mr. Ray here. With our next lesson in grade 12 data management. We're continuing on in our first unit, which is the counting unit, which we're calling permutations and combinations. We've spent the last two lessons looking at permutations. Permutations is the number of arrangements of a certain number of objects. And when you talk about arrangements or permutations, the order is important. Okay, so if you think about things like taking a picture where you're lining people up in specific positions, or you're picking people for specific jobs, that's when you use permutations. Today we're going to look at combinations. Combinations is when you select them and order is not important. So for example, if you're just trying to, select a certain number of people to form a committee, or certain, number of cards from a deck of cards where the order that you choose them does not matter. Okay, so that's what we're looking at today. So whenever you get a question, and it's a counting question, the first thing you ask yourself is the order that I select these things important or not? Because that will help you determine, is this a permutation or a combination? Now, combination, since the order is not important, you're going to have fewer combinations than you would have permutations. So if you look at the formula here, so we use the same familiar notation here with a capital C for combinations, and you've still got the N and the R, so you're selecting from N objects or N people or N cards. That's the total number you have available, and you're choosing R of them. So how many combinations or choices do you have with that combination? You can also write it in this notation, C bracket N comma R bracket. That should be a comma between the N and the R. Either way of these is totally fine. Now, if you compare the combination to the permutation, I've just mentioned that you're going to have fewer combinations using the same values of N and R as you would with a permutation, and this actually shows you that depending on what your value of R is, you're going to have a factor of R factorial more permutations and combinations. So if you know the number of permutations, you just divide that by R factorial, because those things you chose, those R things you chose, could be arranged R factorial ways. So in order to take the order out of the permutation, so that order is not important, you could just divide by that. So if you kind of expand the n pick R, n pick R is n factorial over n minus R factorial. So if we further divide by R factorial, this is our big formula for combinations. Now, the order that you put these does not matter, but you do notice that the two numbers that you're taking factorial of, they actually do add up to n. So if it was 8 choose 2, it'd be 8 factorial over 6 factorial 2 factorial, or you could put 8 factorial 2 factorial 6 factorial. It's easy to check if you did the subtraction right, because the two numbers on the bottom should add up to n. Okay, and again, just like we saw with permutations, we can also combine multiplicative and additive counting principles when we're working with combinations. And again, the key words there are and suggests that it's going to be you're going to be multiplying, and if it's or, you're going to be adding your values that you calculated. Okay, so let's do some examples here. So let's, this is a situation we're going to be looking at permutations and combinations. So in how many ways could Alana, Barbara, Carl, Dominic, and Edward, A, B, C, D, E, fill the positions of president, vice president, and secretary. So these are important. These are specific roles for when we pick these people. So the order does matter that we pick them, because maybe one combination we could pick Alana, Barbara, Carl. Another one would be Barbara, Alana, Carl. Those are same people chosen for those positions, but obviously it's different. We want to make those we want to include both those options where the order is kind of moved around with those three people. So let's look at, well, we've got three positions here. So that's our value of R, and we're choosing from Alana from these five people. So we've got N equals 5, R equals 3. And then when we have to decide, is this a permutation or combination? Well, we can quite easily determine that the order matters that we for selecting, so therefore it's a permutation. So we're going to use the formula for permutation. So the number of ways that we could fill those positions from those five people would be 5 pick 3, P for permutation, and that's going to be equal to 5 factorial over 5 minus 3, or 2 factorial. Okay, and we could reduce that down to 5 times 4 times 3, or you could just do it on your calculator, and the answer to that is 60. So there's 60 ways that we could take those 5 people and assign 3 of them those positions. So there'll be 2 people not chosen at any given way, for any given way. Okay, so we're going to change the question around now. How many ways could these same 5 people form a committee with 3 members? So the fact we're actually doing a committee, that tells us, well, it's the same 5 people with the 3 members, so it's still N equals 5, R equals 3. But this time the order doesn't matter. It doesn't matter if I pick Alana, Barbara, Carl in that order, or Carl, Barbara, Alana for that committee. It's the same 3 people in the committee, so we want to so the order does not matter. Order does not matter. So therefore it's a combination. Okay, so the number of ways we can select the committee is going to be combination with N5 R3, so that's, this time it's 5 choose 3, combination of 3 from 5. So the formula is a little different, so it's going to be 5 factorial over 2 factorial, but we also have the we also have the R factorial. So you can see the difference in the formulas. We're basically taking what we had permutations, so there's 60, and we'd be dividing by 3 factorial. So if we just did the raw math here, you could see this is going to be 5 times 4 is left over from 5 factorial over 3 factorial. 2 factorial is 2, so that's just going to be 10. So there's only 10 ways to form a committee of 3 from these 5 people. There's 60 ways of filling the 3 positions. Okay, so hopefully that shows you the reasons why, and the fact that the combinations for the same N and R values will be lower by a factor, and that factor will be it'll be R factorial. So, and that's what this question here is asking: how are the numbers of ways in parts A and B related? So I make this official sounding, to change a permutation, which is what we had in part A, to a combination, which is what we had in part B. You divide the answer from the permutation by R factorial. So in our case, we took our answer of 60 and we divided by r factorial, and r was 3 for both of them. So 3 factorial. 3 factorial is 6. So 60 divided by 6 is equal to 10. So the factor is, you could say it's, a factor or divisor. The permutation will be r factorial times bigger, in this case 10, and you would divide the permutation by r factorial to get the combination. So that's our factor either way. Okay, so hopefully that makes sense how you compare the two types of counting methods. Very important that every time you get a question you ask yourself, is the order of this answer important or not? Okay, so let's look at some more examples. We've got how many different sampler dishes with 3 different flavors could you get at an ice cream shop with 31 different flavors? Okay, so this is basically saying the ice cream store's got 31 flavors. They give out sampler dishes with three of those 31 flavors. How many different sampler dishes would there be? So right away you could say, does it matter if a sampler is chocolate, vanilla, strawberry, or strawberry, vanilla, chocolate? In that order, it's the same sampler dish as far as we're concerned. So in here the order is not important. So therefore it's a combination. Okay, and our values would be, we're choosing from 31 potential flavors, so that's our n value, 31, and each sampler dish is, you're choosing 3 flavors, so that's r equals 3. So the number of samplers is equal to 31 choose 3. Okay, and 31, if I wrote this out, now there's different ways you can do this. You can, there are many calculators out there that have a button for permutations and combinations. So you might save yourself some time. See if you have that, you would be entering probably the 31 first, and then the combination button, and then the 3, and then equals, and it would give you the final answer. So that's the quickest way, but you can still do this without those buttons. Just take your an extra 20 seconds or so. So this is going to be 31 factorial over 31 minus 3 factorial, which is 28 factorial, and then r factorial is 3 factorial. Okay, so we could actually reduce the 31 and the 28. So on top I will have the 31 times 30 times 29. And on the bottom I'd have 3 factorial, which is 6. Okay, and then probably do this on the calculator. Unless you're really good at mental math, this would be 4495 different samplers. Okay, so that should be straightforward. It's just a matter of, first of all, determine that it's a combination. Big hint in the example title, but you're going to need to do that every time. It's not going to usually tell you this is a combination. It's going to tell you that indirectly through the words. Okay, next question. A ballet choreographer wants 18 dancers for a scene, and then we've got 2 parts. In how many ways can the choreographer choose the dancers if the company has 20 dancers or if the company has 24? So there's really 2 parts here to this question. But the first thing we got to ask ourselves again, even though it kind of tells you, the order of these dancers important. So it's basically 18 dancers per scene. You assume that there's no specific roles. It's just the whole group. So in this case, we'll make the assumption order is not important. You don't have to write this every time. I just want to make sure this is part of your thought process. So order is not important, therefore it's a combination. And then combination. So I'm going to split this into 2 different calculations. One for 20 dancers and the other one here is with the 24 dancers. Okay, so for the 20 dancers, you're choosing from 20, so that's your N value, and in both questions you're choosing 18, so that's your R value. So the number of ways for this first option from 20 dancers would be 20 choose 18. So that's 20 factorial over 18 factorial 2 factorial. Doesn't matter the order you put those. You could see the 20 18 factorial. It's going to leave you with 20 times 19 on the top, and then 2 from the 2 factorial on the bottom. So that gives you 380 divided by 2 is 190. So there's 190 ways of choosing choosing 18 dancers from 20. Probably seems more than you would expect, since there's really only 2 dancers you're not choosing. Let's do the same question from using 24. So what changes here is your N value has now increased to 24. R value is still 18 because you're choosing 18 dancers for the same scene. So the number of ways this time, and again it's going to be combination, is 24 choose 18. So that works out to 24 factorial, 18 factorial, 6 factorial. So this is probably something you do on your calculator, but if you want to do it the part manual, part calculator method, the 24 and the 18 factorials will reduce to 24 times 23 times 22 times 21 times 20 times 19. That's, it's probably a good indication to do it directly at the calculator. But 6 factorial, which stays on the bottom, is 720. And when you do that math, you get a much bigger number of 134,596. Okay, so back to the question. The choreographer has 190 options if they're starting with 20 dancers, but basically 134,500 if they're choosing from 24 dancers. So how would you advise the choreographer to choose the dancers? Well, obviously you don't want to go through even this situation where you try all 190 combinations and see which one works best. This one here would be absolutely impossible to do. So what's a better method of doing that? Well, if you think about it, when you're choosing 18 out of 20, you're really just saying which 2 aren't we selecting? And that's an interesting thing, and you'll see it in the homework questions as well. If I was choosing 2 dancers from 20, I would have exactly the same formula here, because I'd have R and N minus R factorial, which works out to the same denominator. If you think about, you're basically choosing which 2 dancers do we not want. There's probably a better way of choosing your 18 dancers. So decide which 2, in this case, what's starting from 20, or 6, if you start from 24, dancers not to use based on talent or suitability. Suitability for the scene. Okay, so that's just basically, these numbers, tell you right up front. There's no point in trying all the combinations, see which one works best. Probably a better way just to look at your 2 least experienced or least suitable dancers, and or 6 in this case, to choose your 18. Okay. All right, last page here. We've got example where we're going to start using some counting principles. So if you remember, the counting principles are additive and multiplicative. So let's see how that works. For this, Ursula runs a small landscaping business. She has on hand 12 kinds of rose bushes, 16 kinds of small shrubs, 18 kinds of evergreen seedlings, and 18 kinds of flowering lilies. In how many ways can Ursula fill an order if a customer wants? So the first part A is customer wants 15 plants or flowering varieties consisting of 4 roses, 3 shrubs, 2 evergreens, and 6 lilies. Okay, so we're going to break this down. We're going to find the number of ways for choosing, first of all, 4 roses, number of ways to choose 3 shrubs, number of ways to choose 2 evergreens, and 6 lilies. These will be separate calculations. So number of ways to choose the roses. Okay, so that's going to be, so we've actually got 12 kinds of roses to choose from, and we're selecting 4 of those. So that's 12 choose 4, which is 12 factorial over 8 factorial, 4 factorial. That works out to 495. Okay, so we've got 495 ways to choose just the 4 roses. How about the shrubs? Number of ways to choose the shrubs. So again, these calculations are totally dependent of each other at this point. So we've got 16 kinds of shrubs, and we want to choose 3. So that's going to be equal to 16 choose 3. So if you put that down on paper, 16 factorial over 13 factorial, 3 factorial, that works out to 560. All right, let's move to the next one. That's the evergreens. So the number of ways to choose evergreens. Okay, we've got 11 kinds to choose from, and we're picking 2, so that's 11 choose 2, which is 11 factorial over 9 factorial, 2 factorial. That works out to 55. Okay, and finally, number of ways to choose the lilies. Okay, so we've got 18 types to choose from. We're picking 6, so that's 18 choose 6. So this number is probably going to be bigger. We've got 18 factorial over 12 factorial, 6 factorial, and this is a lot bigger, 18,564 ways to choose the lilies. Okay, so we didn't answer the question yet, but we've got the building blocks for it. We've got the number of ways to choose each of these independently, but the customer wants all of these. He wants 4 roses and 3 shrubs and 2 evergreens and 6 lilies. You notice I'm emphasizing the word "and" between them. So this is, I could just circle that one "and," but there are implied "ands" between all of them. So the "and," it's "and not or." So therefore we're going to multiply. It's a multiplicative principle of counting. So total number of ways. So this is the number of ways to do all of these selections. So because this is the multiplicative, it's "and," we're multiplying all these numbers together. So that's 495 times 560 times 55 times 18,564, and that is a pretty humongous number, 283,026,744,000. So lots of options for that customer. Okay, so again, we're looking, we looked at each of the number of ways for each of them individually, and then determined is this going to be additive or multiplicative? Depends on the words and or. Okay, now in this case, you can see part B says either 4 different roses or 6 different lilies. Okay, so right away, based on what we just did, you can see this is going to be different. This is going to be adding them together. So again, let's figure out how many ways can we do each of these independently. So the number of ways to choose the roses, it's not the same as the one above because we're actually choosing 4 roses. Actually, is it the same? Yeah, it is the same number. So so that's going to be, again, we had 12 roses to choose from. So 12 choose 4. And we already did that up here. 12 choose 4 is 495. And then the number of ways to choose the lilies. Okay, we've got 18 kinds of lilies to choose from, and we want 6, so 18 choose 6. And again, we just did that up here, so let's steal that answer, 18, 5, 6, 4. Now, what do we do with them? Well, we've already talked about it. So this is or, not and. So therefore, we're going to add, because it's the additive property of counting due to the word or, one or the other. You don't multiply them. So in this case, the total number of ways is equal to these two numbers added together, 495 plus 18,564. That's equal to 19,059 ways. Okay, so that's a good, well, we practiced the combinations with there. If you could try those out, this homework's actually pretty quick, but hopefully, for sure, the important thing here is not only learn the formulas, but learn when to use permutations and when to use combinations. And on top of that, we still have our additive and multiplicative counting principles on top of each of those. Okay, so next lesson we'll be looking at a little bit further work with problem solving with combinations, and we'll finish up with combinations at that point. The work we're doing in this unit, it actually carries over into when we do probabilities. You're still going to have to use calculate combinations and permutations in that unit as well. So very important skills to have going forward. Okay, that's it for today, and we'll see you on the next lesson. Have a good day.